Hello, my name is Morgan Shetty Byers, and what I am doing here is trying to simplify very complex cosmology papers so that anyone can follow along. Even if they have never studied physics, we start with primordial magnetic fields. These are the invisible structures that scientists think may have been created either during inflation or during later phase transitions in the very early universe. If you imagine the universe as a giant ocean, inflation would be like a sudden storm stretching the water surface smooth and wide, while phase transitions would be like frozen patches suddenly forming and expanding. Both processes concede magnetic fields. Then we have quantum fluctuations. These are tiny random wiggles in energy that happen during inflation because quantum mechanics says the vacuum is never truly empty. These fluctuations were stretched by inflation to cosmic scales. They later became the seeds of galaxies and also possibly magnetic fields, so quantum randomness is written into the structure of the universe itself. Next, the phase transitions imagine water cooling into ice, but happening with fundamental forces of nature at different times in the early universe. One of those transitions could have produced bubbles like ice nucleation. These bubbles grow, collide, and merge, and inside them, magnetic fields can be created. This is how the analogy of crystal growth and isotropic expansion connects to cosmology because each bubble expands in all directions equally. Now, magnetic fields are tricky to trace because we cannot see them directly, but scientists simulate their evolution using magnetohydrodynamics, and they find that inflationary seed fields and phase transition seed fields evolve differently over billions of years in galaxy clusters, filaments, and cosmic voids. That difference remains like a fingerprint. So, if we can measure it with rotation measures of light from distant galaxies, we can tell which origin story is correct. There is also the idea of instabilities, for example, the Weibel instability, which is when charged particles in hot plasma stream in different directions and create currents. This instability could amplify magnetic fields after inflation and prevent them from fading away due to expansion. This is similar to how a ferrofluid forms complex patterns when you put a magnet near it. Fields and particles dance together, and disorder creates new structure. And then there is the connection to gravitational waves. Some models say that primordial magnetic fields could leave an imprint in the spectrum of gravitational waves. These are ripples in space-time itself, so by detecting the right signal, we might actually measure ancient magnetic fields from the dawn of time. So what I did was to take these papers and think in analogies. Laminar flow for smooth expansion ice nucleation, for isotropic bubble growth, ferrofluids, and copper coils for thermodynamic randomization through electromagnetic induction. In this way, the story of the universe can be told like a series of familiar physical processes, but happening on unimaginable scales. The takeaway is that the expansion of the universe, its isotropy, and the tiny seeds of randomness that became galaxies can all be understood as a layered interplay between smooth, stretching, sudden transitions and fluctuating fields. By blending these ideas, we can bring the cosmos closer to human imagination.